For centuries, classical physics offered us a deeply comforting view of reality. Following the laws of Isaac Newton, science treated the universe like a giant, flawless clock. If you knew the starting position and speed of an object, you could use math to perfectly predict where it would go. But in the first few decades of the 20th century, that perfect clockwork model fell apart. When scientists began looking closely at the fundamental building blocks of reality, trying to carefully observe the exact behavior of light and matter, the deterministic rules of classical physics completely broke down. This shift reached a crossroads in 1927. The world's leading physicists met in Brussels to make sense of this bizarre microscopic behavior. Out of these debates emerged quantum mechanics, a theory making a highly uncomfortable claim. At its deepest level, reality is not fixed or predictable. Instead, the universe is governed entirely by chance, probability, and statistics. This animation illustrates one of the strangest new rules, superposition. Until the exact moment it is observed, a fundamental particle doesn't exist in one specific location. It exists as a blurry cloud of multiple potential outcomes. The act of measuring the particle is what forces that probability cloud to collapse into a single, defined point. Many scientists, raised on absolute certainty, resisted this idea. Albert Einstein famously rejected the probabilistic nature of the new theory, declaring that he did not believe God plays dice with the universe. And yet, this creates a fascinating paradox. How did a branch of science built entirely on randomness, uncertainty, and blurry probabilities end up giving us the most exact, hyper-precise measurement tools in human history? As the decades passed, physicists stopped fighting the weirdness of the quantum realm and started engineering it. They realized that you could harvest this microscopic unpredictability to build technology that measures our world with extreme accuracy, starting with time. As we see in this simplified atomic model, modern atomic clocks work by manipulating elements like cesium or strontium. A laser forces the electrons inside these atoms into a state of superposition, meaning they are both excited and unexcited simultaneously. This creates a microscopic quantum pendulum, swinging back and forth millions of billions of times per second. Because an electron can only absorb a photon if it has exactly the right amount of energy to jump between those specific levels, that reaction creates an incredibly consistent resonant frequency. That specific signature provides an unchanging, universal baseline to define exactly how long 1 second actually is. This quantum timekeeping runs the logistics of our modern world. It serves as the literal foundation for the Global Positioning System, or GPS, guiding billions of cell phones every single day. When you pull up a map, your phone is communicating with a network of over 30 orbiting satellites, each carrying multiple atomic clocks. By comparing hyper-precise timestamps beamed down from space, your phone calculates exactly how long the signals took to arrive, triangulating your exact physical distance from those satellites. Without the reliable tick of a superpositioned electron, those distance calculations drift. Our ability to navigate the physical world with absolute certainty only exists because we surrendered to the unpredictable rules of the quantum realm. Beyond the electron, humanity also learned to master the photon. A standard light bulb produces light through thermal energy, causing atoms to spit out photons chaotically in all directions and across many wavelengths. Laser light, however, is perfectly uniform and organized. This diagram shows the quantum mechanics behind lasers, a process called stimulated emission. When an excited atom is hit by a specific photon, it drops to a lower energy state and spits out a cloned, identical photon. Trapped between mirrors, this triggers a massive chain reaction, resulting in a unified, highly concentrated beam of pure light. We have scaled that quantum engineering up to massive proportions. This is LIGO, the Laser Interferometer Gravitational Wave Observatory. Scientists use hyper-stable lasers housed inside these 2.5-mile concrete arms to hunt for tiny ripples in the fabric of space and time. LIGO splits a single quantum laser beam, sending half down each arm. When a gravitational wave passes through the Earth, it physically stretches and compresses space itself. By measuring how that distortion shifts the phase of the laser light, physicists can detect changes in distance smaller than a single proton. In 2015, that extreme quantum exactness captured the most powerful event human beings had ever recorded. LIGO detected the gravitational waves of two massive black holes violently colliding in deep space. Mastering the physics of a single photon is what allows us to observe these massive events billions of light years away. Today, researchers are pushing into an even stranger frontier, quantum entanglement. This is a phenomenon where particles share a state and act as a single entity, even when separated by vast distances. It is a concept so bizarre that Albert Einstein derisively called it spooky action at a distance. But spooky action is no longer a theoretical debate. Inside facilities like the IBM Research Lab in Yorktown Heights, scientists are actively engineering entanglement into physical computing hardware. As this visualization shows, a classical computer bit is like a light switch. It can only ever be set to 0 or 1. A quantum bit, or qubit, uses superposition to exist as a combination of both states simultaneously, allowing it to plot data anywhere across a 3D surface and explore multiple mathematical possibilities at once. The true power arrives when these qubits are entangled. By linking dozens of qubits together, a single machine generates computational complexity so fast that describing it completely would require you to write down more bits than there are atoms in the visible universe. Modern quantum computers do not try to eliminate the chaotic, probabilistic nature of the quantum realm. They explicitly exploit that chaos to process information in ways that classical computers simply cannot match. A century ago, the greatest minds in science balked at the idea of a universe governed by chance. But today, the probabilistic math of quantum mechanics stands as the most rigorously tested and highly successful scientific theory we possess. The equations drafted in 1927 are the invisible scaffolding of modern civilization. They are hardwired into the transistors inside your laptop, the atomic clocks in orbit, and the fiber optic cables crossing the ocean floor. The quantum realm feels deeply unintuitive to us, but the universe is not obligated to conform to human common sense. We have to rely on observation, even when the results are deeply strange. Humanity did not reach the stars, map the planet, or build modern computing by forcing reality to be perfectly predictable. We did it by finally learning how to play dice with the universe.